Hello friends, I am Amul Sonone. In this video, we'll discuss what is meant by cyclic permutation, is which permutation we have to call as a cyclic permutation. We'll also see even permutation and odd permutation. Let's see definition of cyclic permutation. See, in previous video, we have discussed definition of permutation, examples of permutation in detail, right? Before watching this video, please watch previous videos. Okay, let's see definition of cyclic permutation. Let A be a non-empty set. Okay, then a permutation f of the set A is said to be a cyclic permutation. Is said to be a cyclic permutation if there exist some elements A1, A2 up to AK of A such that f of A1 is A2, f of A2 is A3, f of A3 is A4, f of AK minus 1 is AK, f of AK is equal to first element A1 and f of x is equal to x if x is element of A but x is not element of the set A1, A2, AK. Means the elements of A other than A1, A2, AK maps to itself. Okay. Then that permutation is called as a cyclic permutation, and that cyclic permutation is denoted by f is equal to in round bracket A1 comma A2 up to AK, or sometimes it is denoted by A1, A2 up to AK. Since the cyclic permutation contains k elements, it is also called as a cycle of length k, cycle of length k. Means a cyclic permutation involving k elements like a1, a2, ak is called as a cyclic permutation of length k or a cycle of length k. Let's see example of cyclic permutation. For example, suppose we have a set A containing elements 1, 2, 3, 4, 5, 6, and 7. Okay. And F is equal to a permutation in which 1 maps to 1, 2 maps to 4, 3 maps to 7, 4 maps to 3, 5 maps to 5. Okay. 5 maps to 5, 6 maps to 6, and 7 maps to 2. Let's check whether it is cyclic permutation or not. See, there are some elements, they are mapping to themselves. Means 1 maps to 1, 5 maps to 5, 7 maps to 7. Right? There are some elements, they are mapping to themselves. F of 1 is 1, F of 5 is 5, and F of 6 is 6. There are some elements, they are not mapping to themselves. For example, F of 2 is mapping to 4, F of 4 maps to 3. Okay, F of 3 maps to 7, and F of 7 maps to 2. Means here, okay, means 2 maps to 4, 4 maps to 3, 3 maps to 7, and 7 maps to 2. Therefore, we can consider this as cycle, and we can write it is equal to F. Right? And remaining elements 1, 5, 6 are mapping to themselves, so no need to write in the cycle. Okay, means here we can write F as a cyclic permutation in which 2 maps to 4, 4 maps to 3, 3 maps to 7, and 7 maps to 2. And we can consider that it is a cyclic permutation of length 4. There are 4 elements involved in this cycle: 2, 4, 3, 7. Therefore, we can say that this is a cyclic permutation or a cycle of length 4. Okay. We can note that let A be a finite set then every non-identity permutation of A. Non-identity permutation means identity permutation means a permutation in which every element maps to itself. Non-identity permutation means there exists at least one element in that permutation which is not mapping to itself. Okay. Every non-identity permutation of A is either a cycle or product of disjoint cycles. Either a cycle or product of disjoint cycles. We have seen example of cycle, right? This F is a permutation of set 1, 2, 3, 4, 5, 6, 7. It is a cycle. Okay. There may be some permutations which are not cycle. And this result says that if you have any non-identity permutation which is either cycle or a product of disjoint cycle, this product stands for composition. Here we have to take meaning of product of disjoint cycle means composition of disjoint cycles. Okay, let's see example of permutation which is not not a cycle. Okay, suppose we have a set A is equal to same set 1, 2, 3, 4, 5, 6, 7, and we consider one permutation of A in which 1 maps to 1, 2 maps to 5, 3 maps to 6, 4 maps to 4, 5 maps to 7, 6 maps to 3, okay, and 7 maps to 2. Yeah, it is a permutation of this set A. Then we can write F as. See, note that F is not a cycle. It does not satisfy the definition of cyclic permutation. Okay, but we can write F as. See, consider a cycle in which 2 maps to 5, 5 maps to 7, 7 maps to 2, means here this cycle is completed. But there are elements other than 2, 5, 7, they are not mapping to themselves, which are 3 and 6. See, means we have tried another cycle in which 3 maps to 6, and here 6 is mapping to 3, so this cycle is completed. See, other than 2, 5, 7, 3 and 6, 1 and 4 are mapping to themselves, so no need to write here. Okay, so you can see that if we have expressed composition of two cycles, disjoint cycles, means, or we can consider composition of product of two disjoint cycles. We can also write F as composition of these two cycles, 3, 6, 2, 5, 7. Okay. Let's see next definition. Transposition. Let's see what is meant by transposition. Transposition means any cyclic permutation of length 2, or you can say that any cycle of length 2 is called a transposition. For example, suppose we have a set having elements 1 2 3 4 5. Then here you can say that if permutation f in which 2 maps to suppose 5 and 5 maps to 2 and remaining all elements maps to themselves. So you can say that f is a cycle of length 2, means it is a transposition of A. You can write another transposition. Suppose 4 comma 3 means it is a permutation in which 4 maps to 3, 3 maps to 4 and remaining all elements maps to themselves. Okay. Note that the transposition 2 comma 5 is same as 5 comma 2 and 4 comma 3 is same as 3 comma 4, because 2 comma 5 is a permutation in which 2 maps to 5, 5 maps to 2 and remaining all elements maps to themselves, and similarly in 5 comma 2 5 maps to 2, 2 maps to 5, remaining all elements maps to themselves. Therefore 2 comma transposition 2 comma 5 is same as 5 comma 2. Similarly 4 comma transposition 4 comma 3 same as 3 comma 4. Okay, means any cycle of length 2 is called a transposition. Okay, let's see next result. Note that every cycle of length greater equal 3 can be written as product of transpositions. Let's see example. Suppose we have a set A 1 2 3 4 5 and a cyclic permutation of length suppose 4, 2 maps to 4, 4 maps to 3 and suppose 3 maps to 5. This is cyclic, this is cycle of length 4. See, we can write f as, see, we can write this f as a product of transpositions two comma 5 composition 2 comma 3 composition 2 comma 4 2 comma 5 composition 2 comma 3 composition 2 comma 4, or we can also write f as 2 composition 4 composition 4, composition 3, composition 3, composition 5. Yes, this cycle of length 4 we can write product of this transposition. There are two ways to write, 1 and 2. Let's verify it. We have a cycle of length 4. Okay, we have written f as 2, composition 5. Sorry, transposition 2, 5, transposition 2, 3, and transposition 2, 4. Okay, 2, 5. Here we have set A is equal to 1, 2, 3, 4, 5. Okay. See, transposition 2, 5 means it is a permutation in which 2 maps to 5 and 5 maps to 2. Remaining all elements are mapping to themselves. Okay, composition. 2, 3 means transposition 2, 3 means it is a permutation in which 2 maps to 3, 3 maps to 2. Remaining all elements are mapping to themselves. And transposition 2, 4 means it is a permutation in which 2 maps to 4, 4 maps to 2, and remaining all elements are mapping to themselves. Okay. I'm writing first permutation as it is. Composition. And this permutation is product of these two permutations. Okay. See, in this permutation, I'm writing this permutation as a product of second and third permutation. In 1 maps to 1, 1 maps to 1. So here 1 maps to 1. 2 maps to 4, 4 maps to 4. So 2 maps to 4. 3 maps to 3, 3 maps to 2. So 2 maps to 3 maps to 3, 3 maps to 2. So 3 maps to 2. 4 maps to 2, 2 maps to 3. So 4 maps to 3. And 4, 5 maps to 5. And here also 5 maps to 5. So here 5 maps to 5. Okay. Okay. Now I'm writing this permutation as a product of these two permutations. In this permutation, 1 maps to 1. Here 1 maps to 1. So here 1 maps to 1. 2 maps to 4. 4 maps to 4. So here 2 maps to 4. 3 maps to 2. 2 maps to 5. So here 3 maps to 5. 4 maps to 3. 3 maps to 3. So here 4 maps to 3. 5 maps to 5. 5 maps to 2. So here 5 maps to 2. Yes. And we can write this permutation as here 1 maps to 1. So no need to write in terms of in the form of cycle. Here 2 maps to 4. 4 maps to 3. 3 maps to 5. And 5 maps to 2. Yeah, and this is equal to F. Means we have verified that a cycle in which 2 maps to 4, 4 maps to 3, 3 maps to 5. We can write product of these three transposition, these three transposition. Similarly, we can verify that product of transposition 2, 4 4, 3 and 3, 5 is equal to a cycle in which 2 maps to 4, 4 maps to 3, 3 maps to 5. That is equal to it. Okay. Means we have two things. First, every non-identity permutation is either a cycle or product of disjoint cycles. And just we have verified, we have seen that every cycle of length greater equal 3 can be written as product of transpositions. Yes. By combining these two results, we can conclude that every non-identity permutation is either a transposition or product of transpositions. Every non-identity permutation can be written as, this is more appropriate, can be written as either a transposition or product of transpositions. Yes. Let's see some examples. Suppose set A is 1, 2, 3, 4, 5, 6, 7. Okay. Okay. I am taking one permutation F of set A, in which 1 maps to 6, 2 maps to 5, 3 maps to 4, 4 maps to 1, 5 maps to 7, 6 maps to 3, which element left? Okay, 7 maps to 2. Therefore, we can write F as, in terms of cyclic form, 1 maps to 6, 6 maps to 3, 3 maps to 4, and 4 maps to 1. So this cycle is completed. Okay. Next, 2 maps to 5, 5 maps to 7, and 7 maps to 5. Sorry, 7 maps to 2. Okay. This cycle is completed. Okay. Therefore, we can write this F as in terms of transposition. At transposition 1,6, composition, so not one, transposition 1,4, transposition 1,3, transposition 1,6. I have written this cycle as a product of these 3 transpositions into composition. Now I'm going to write this cycle as a product of transpositions 2,7 and 2,5. I have written this cycle as product of these 2 transpositions. Here we have written this permutation F as a product of 5 transpositions. Yes, let's see another example. Consider another permutation of set A. In which 1 maps to 5, 2 maps to 7, 3 maps to 2, 4 maps to 1, 5 maps to 4, 6 maps to 6, 7 maps to 3. Okay. Yes. Therefore, we can write G as in terms of cyclic form 1 maps to 5, 5 maps to 4, 4 maps to 1. So this cycle is completed. Okay. Composition 2 maps to 7, 7 maps to 3, and 3 maps to 2. Okay. So this cycle is completed. And here 6 maps to 6. So no need to write 6 here. Okay. Just now we write these cycles as product of transposition. 1 maps to 4, 1 maps to 5. I have written this cycle as product of these 2 transposition. This composition transposition 2, 3, composition 2, 7. I have written this cycle as product of these 2 transpositions. Okay. Means here we have written permutation G of set A as a product of 4 transpositions. In general, we can write any non-identity permutation as a transposition or product of transposition. Okay. Let's see definition of even and odd permutation. Even permutation definition. A permutation is said to be even permutation if it can be written as product of even number, this is important, even number of transposition. And similarly, we can define or permutation. A permutation is said to be odd permutation if it can be written as product of odd number of transpositions. See, we have seen every non-identity permutation is either a transposition or product of transpositions, right? A permutation is said to be even permutation if it can be written as product of even number of transpositions. An odd permutation means a permutation. Odd permutation means a permutation. We can write it as a product of odd number of transpositions. See, here we have seen two examples of permutations of A. Here we have written F as a product of 5 transpositions, and 5 is odd. Therefore, F is odd permutation. And we have written G as a product of 4 transpositions, and 4 is even. Therefore, G is even permutation. Okay. Note that identity permutation of any non-empty set A is an even permutation. Identity permutation is always even permutation. You can say that suppose set A containing n elements 1 to n, and suppose F is a permutation in which 1 maps to 1, 2 maps to 3, 2, 3 maps to 3 maps to 3, n maps to n. Then F is an identity permutation of A. Okay. You can see that you can write F as product of two transposition in which one maps to 2 and 2 maps to 1. We can write it, verify. Means we have written F has a product of two transposition, therefore F is even permutation. Okay. Let's classify even and odd permutations of a set having three elements 1 to 3. The set of all permutations of a set 1 to 3 is, we have already seen, it is S3 and it contains permutations, permutation in which 1 maps to 1, 2 maps to 2, 3 maps to 3, 1 maps to 2, 2 maps to 3, 3 maps to 1, 1 maps to 3, 2 maps to 1, 3 maps to 2, 1 maps to 1, 2 maps to 3, 3 maps to 2, 2 maps to 2, 1 maps to 3, 3 maps to 1, 3 maps to 3, 1 maps to 2, 2 maps to 1. Okay. We have to classify the even and odd permutations of from this S3. Okay. We can write, see, we have seen any identity permutation is even permutation. Yes, means it is even permutation. Let's take second permutation in which 1 maps to 2, 2 maps to 3. We can write this permutation as in terms of cycle as 1 maps to 2, 2 maps to 3, and 3 maps to 1. So this is completed, and we can write this cycle as product of transposition 1 3 and 1 2, and we have written this permutation as a product of two transpositions, therefore this is also even permutation. Yes, let's take third permutation, a permutation in which 1 maps to 3, 2 maps to 1, 3 maps to 2. We can write this permutation as a cycle in which 1 maps to 3, 3 maps to 2, and 2 maps to 1, and we can write this cycle as a product of transposition in which 1 maps to 2 and 1 maps to 3. Yes, we have written this permutation as a product of two transpositions, so it is also a even permutation. Okay, let's take fourth, a permutation in which 1 maps to 1, 2 maps to 3, 3 maps to 2. In this permutation, 1 is mapping to 1, 2 maps to 3, and 3 maps to 2. So it is completed. Means we have written this permutation in terms of single transposition. Yes. So it is odd permutation. Similarly, fifth is odd permutation, sixth is also odd permutation. Means in S3 there are 3 even permutation and 3 odd permutations. Okay. Means exactly half of are even permutation and half are odd permutations. Let A and B a set of all even permutations in Sn. Means Sn contains even as well as odd permutations. I am collecting all even permutations in the set An. Then you can observe that cardinality of An means number of elements in An is exactly half of the number of elements in Sn, and Sn contains n factorial elements, so An contains n factorial by 2 elements. For particularly n is equal to 3, A3 contains 3 factorial by 2 elements. 3 factorial is 6 and 6 by 2 is 3. And see, in S3 there are exactly 3 even permutations. Therefore, we can write A3 is a set containing 3 permutations. 1 maps to 2, 2 maps to 3, 3 maps to 1. 1 maps to 3, 2 maps to 1, and 3 maps to 2. Yes. Note that product of 2 even permutations is even permutation. Means if you take product means composition of any 2 even permutation is again an even permutation. 2 product of 2 odd permutations is even permutation. Product of an even and an odd permutations is odd permutation. The proof is very simple. It's fluid. Let F and G be any 2 permutations of the non-empty set A. Let F and G be written as K and M number of transpositions respectively. Then you can note that F composition G or product of F and G is written as K plus M number of K plus M number of transpositions. Means F and G are permutations of A. F and F is written as K number of transposition, G written as M number of transposition, then F naught G is written as K plus M number of transposition. You can see it here. Here F is a product of 5 transpositions. G is a product of 4 transpositions. So we can write F naught G as a product of 9 transpositions, which are 1, 4, 1, 3, 1, 6, 2, 7, composition 2, 5, composition 1, 4, composition 1, 5, composition 2, 3, composition 2, 7. F composition G written as product of 9 transpositions. F is written as product of 5 transposition, G is written as product of 4 transposition, and F naught G written as product of 5 plus 4, 9 transpositions. Yes, means here, if both F and G are even permutation, then K and M both are even numbers. And if K and M are even numbers, K plus M is also even, means F naught G is even permutation. Note 2. If F and G are odd permutations, then both K and M are odd integers, and addition of odd integers is even integer, means K plus M is even. So F naught G is even permutation. Note 3. Suppose F is even permutation and G is odd permutation, then K is even, M is odd, and addition of even and odd integer is odd. So F naught G is odd permutation. And similarly, if F is odd permutation and G is even permutation, then K is odd, M is even, then K plus M will be odd integer, and then F naught G will be odd permutation. Okay, I'm stopping the video. Thanks for watching.